Hi, I'm Elaine. I'm going to talk about Huffman coding, which is a data compression technique. I'm going to show you how to compress this string of text, learn it well. So as you can see, there are 8 bits for each letter, and what we want to do is reduce this down. Now how we do that is we create a binary tree. The binary tree is constructed first by writing down every letter that's in this phrase. So learn is unique, space, and then the D, because we have the A and we have the N here, IT and W. So these are all of the letters in this sentence in the file that we're going to represent. The next thing to do is write next to it the frequency. So 1, 2, 3, 4. So there are 4 L's, there are 3 E's, there are 3 A's, 2 R's, there are 3 N's, 4 spaces, 1, 2, 3, 4 spaces, 1 D, 1 I, 1 T and 1 W. Now we construct a binary tree by writing down the letters at the bottom as the branches. They'll become the branches, and we write them in order. So all of the lower frequency items first, D, I, T, W, and they have a frequency of 1. And then we write next to that the next low value, which is an R, and then we have E, A, N, which are a frequency of 3. Then we have the space, which has a frequency of 4, and then we have the L. So they're all of our letters that we're going to use to construct a binary tree. Now, binary tree has 2 branches for each node. So what we do is we start off with the first 2 branches for I and D, and we give them a frequency of 2, and they represent I and D. We could have put these in any order, it doesn't really matter. Now we cannot add T onto that, so we can't add T onto that because that would give us 3 branches. That would not result in a binary tree. So what we need to do is join these together, and now we have 2 nodes that we can join together to make a further node, and that would allow us to find WTID, and this one's for WT, and the frequency is 4. Again, we cannot join R to WTID or WT because that would give us 3 branches, so we need to join those together, and that gives us a frequency of 5. We can find 5 characters here, and we can join those together with another node. That gives us 9 characters, so we can find E and R, and via this we can find ER, WITD. Now we join 2 further nodes because we cannot add A onto ER, WITD. So we give that a frequency of 6, and again we can join those together to form a new node. So that's NA, and this one is NA, WITD. So we can find, ER as well. So all of these letters can be found via this node, which adds up to 15. And finally, we have 2 more left to join together, and they have a frequency of 8, and that is L space. Now we join those together, add up the frequencies, that's 23. So this is the root and the parent node of the tree, so the parent of the tree. Now, just a quick check, we ended up with 23 here, allowing us to find L space, NA, ER, WITD via these branches. Make that a bit clearer, it's a little messy. So we can find NA, ER, WITD via this root here. So let's just count up how many characters we have. So we have 23 characters, and that matches the root. And here, just to make sure I have the frequencies right, again, they're correct. Now what we do is we label the binary branches with 0, 1 and so on. So the codes for these, what we need to do is now turn each letter into a shorter code. Remember, we don't want to have the 7 or 8-bit code that we have here. We want to have a shorter code. So L is going to be 0, so L is going to be E is going to be found here, so going backwards all the way up there. E is going to be 1100, 1100. Let's tidy that up a bit. 1100. A is going to be found here, so it's 101. Again, what I've done there is I've done 101, so 101, and hopefully you get the point. So it's for R, it's 1101, 1101. For N, it is 100. So for a space, it's 01, and for D, it's 11111. So all of the ones. And for an I, it's all of the ones, but the last one is a 0. And for the T, it's 11101, 11101. And for the W, it's 11100. These are the codes for representing each of the letters as opposed to the 8-bit ASCII. So it's actually 7 bits for the letters, but it's the first one is 0. So the actual codes have been given now. So if you were to learn it well, it would be 0, 0, 1, 1, 0, 0, 101, 1, 1, 0, 1, 100. And then you'd have the space after that, which is 0, 1. Another thing to notice here is each of these values. So for L, for example, the code is not a prefix of any other code in this list. The code for E is not a prefix for any of the others, so there is no ambiguity. So this 00 doesn't appear as a prefix for any of the other letters, therefore it's going to be found as L. And the same for 1100, that doesn't appear as a prefix for the other codes. And the same for 101, that doesn't appear as a prefix for any of the other codes. Same for R, so there's no ambiguity, and that's important, otherwise it could be decompressed incorrectly. So that's Huffman coding. Now the length of 23 characters would be 8 bits times 23, which is, I think it's about 184 bits. And in the case of this, it will be less because we are using fewer bits. So just to be clear on this, we have 4 L's with 2 bits. So that's going to use 4 times 2, which is equal to 8 bits. And I won't write this for all of them. This is going to be 3 times 4, so E will be 3 times 4, and that's going to be 12 bits. A will be 3 times 3, which is 9 bits. R will be 2 lots of 4 bits, which is 8 bits. N will be 3 lots of 3 bits, which is 9 bits. Our space will be 4 spaces with 2 bits for each, so that's 8. And then for each of the others, there are 5 bits and just one of them. So I'm just going to add that to 20 because that's 5 times 4 is 20. Make my maths easier. So 74 bits instead of 184 bits is the compression, which is just a bit over a third. And that's around about the compression rate for, or thereabouts, for most English language sentences. And hopefully that's given you an overview of Huffman coding.